So we have a thin hollow sphere. I is equal to 2/3 mr squared is released from rest at the top of the incline tilted to angle theta. The sphere rolls down the incline to the bottom at a distance d without slipping. Draw a free body diagram. All right, so we want to understand all the forces that are happening on here. So we have gravity, and we have a normal force, because we have a surface touching it. Now, the surface might exert a frictional force, and we know because this thing is rotating around its center of axis, this axis of rotation here, that we have to have a torque, and neither the normal force nor gravity will exert a torque on this thing. So it's not going to roll without slipping unless there's some friction. And because the angular acceleration has to be this way, clockwise, we need a torque like this in order to cause that angular acceleration. So the force of friction is going to be that way. Okay, so that's A. That's our first step, the positional or extended free body diagram. Determine the acceleration. So this is where we're going to do F net equals ma. Now, you have to remember this friction is static friction, so we don't have a formula for it. There's no formula for static friction. Static friction depends on the situation. There's a formula for maximum static friction, but we don't know that the friction is at maximum necessarily, right? So we're going to do F net equals ma first, because we do want the acceleration. And if we make this, generally we make the direction of the acceleration positive. And then we make this our axes. This is x and y. We got to decompose mg into its constituent components, mg sine theta, because this angle here is theta. And then this is mg cosine theta. Okay, so then the net force in the x direction, the net force down the ramp, you have mg sine theta down the ramp, which is the positive direction. And then you have force of friction up the ramp, which is the negative direction. And that equals mass times acceleration. Now, we don't know this. Now, don't do this. Very common mistake to just say the friction's mu times the normal force. One, they didn't give you the coefficient of friction. But if they did, it would not be helpful at all because the friction is not necessarily the maximum static friction. Okay, so what are we going to do instead is look at the net torque equals I alpha, this setup here. Now, from this axis of rotation, the gravity doesn't exert a torque because the r is 0. The normal force is parallel to the r vector. Remember, the r vector is from the axis of rotation to where the force is applied, and it is parallel to the normal force. It's not perpendicular, so it's not going to cause any torque. Only the frictional force exerts a torque. And this is an important thing, is the angular acceleration should be consistent in positive direction with the linear acceleration. That is, if it is accelerating down the ramp, the angular acceleration should be positive in the clockwise direction to make it roll down the ramp. So the torque is force of friction times r, because this distance is the radius, and then it's already at a right angle to the frictional force, is equal to I, which is 2/3 mr squared, times alpha. One of these r's can cancel, and then we recognize that if we roll without slipping, that v equals r omega, and also linear the acceleration of the center mass also equals r times alpha. Okay, so we can replace this r alpha with the acceleration. So the friction was 2/3 ma, which now we can plug into here, and then we can solve for the acceleration. Now the m's can cancel, and you can add the 2/3 a, so you get g sine theta is 1a plus 2/3 a is 5/3 a. And so you get 3/5 g sine theta equals a. Okay, boom. Determine the minimum coefficient of friction necessary for the sphere to be able to roll without slipping down the ramp. So now, at this point, what happens if the coefficient of friction is too small is the maximum the frictional force we need here might exceed the maximum frictional force. So here we have the frictional force equals the maximum. Okay, what is the frictional force? Well, we found the acceleration. We can plug that into here. We know the frictional force is going to equal 3/5, or it's going to be 2/3 times ma. And the acceleration was 3/5 g sine theta. Okay, how about the maximum friction? Is equal to mu s times Fn. Now, the normal force, we didn't do this, but in the y direction, there's no acceleration. So the normal force equals the mg cosine theta, right, from inclined plane. So this is mu s mg cosine theta equals the maximum frictional force. And now we can set these equal to each other, because if you're just about to start slipping, you're just hitting that maximum frictional force. So this is going to be 2/5 mg sine theta is going to equal mu s mg cosine theta. And the mg's cancel, and you get mu s is equal to 2/5. You divide the 2/5 sine theta, just divide the cosine theta over cosine theta. Or you can write it as tangent theta if you want, like that.